Essentially, it means heating using electricity. The concept is pretty simple. When electric current passes through a material, heat is produced. As simple as that. And there can be indirect heating and direct heating. In direct heating, the current is passed through the material itself. In indirect heating, the current is passed through some other material which produces heat, which gets coupled to the material that you want to heat. Okay. We have looked at the various modes of heat transfer already. Electric heating also follows the same modes. There can be conduction, there can be convection, there can be radiation always. In general, any heating phenomenon involves all the three modes, but generally one mode is predominant in most cases. The simplest example of electric heating is the room heater or water heater, where you pass current through a resistive material which dissipates I square R watts and produces the required heat that heats the water. Okay. The total energy, as usual, is power multiplied by time. If power is not constant, then you have to do the integration over time. This is known as Joule heating. Now, one very important distinction when you use the words furnace and oven. There's no mathematical proof for what I'm writing here, but convention is that if the operating temperature is more than 100,000 degree Fahrenheit, then we call it a furnace. Anything below 1000 degree Fahrenheit is known as oven. Okay. Although I have seen people not following this convention all the time. Ovens are obviously lower temperature operation, so they are seen more in homes, while furnaces are obviously more seen in industry. Okay. Don't go by this definition very precisely. This is a rough guideline. Okay, that's it. Direct heating versus indirect. I have already told you several times, but it's written again here. Here they're talking about cooking the food directly over the heat. Okay. And they're assuming non-electric means of cooking right now. So, but the basic idea remains the same. Now, domestic applications of electric heating, there's a long list which I am not going to show you, but I've taken some examples. Room heaters, building heating systems, water heaters, hot plates for cooking, electric kettles, electric iron, electric ovens, electric toasters. You see all these things around you. Okay. For industry, things are little more interesting. Melting of metals uses electricity. Welding uses electricity. Molding of glass uses electricity. Molding of plastic components also uses electricity. Insulators have to be baked to make them better materials. That also is generally done using electricity. High frequency electricity, by the way, not 50 hertz. Plywood, that means furniture, is also generally conditioned by using high frequency electric treatment. Advantages, we have already seen this previously, but let's look at it once again. No pollution almost, low noise, quick response time, accurate control, relatively safe, although chances of electric shock are there. You got to be careful about that. And you can easily transport electric heating to local conditions from one point to another without having to worry too much about setting up the whole thing. Heating is more uniform in case of electric heating compared to other methods. Efficiency is better. Maintenance is much lower here. This we have seen already, so I'm not going to talk too much about it. Conduction, convection, radiation, we have seen the equations for all this. Now, there are many methods of electric heating, and one conventional technique is to divide them into low frequency and high frequency techniques. Low frequency means 50 hertz or 60 hertz. High frequency generally means megahertz or so. Among each category, there are several techniques. Power frequency means 50 hertz or 60 hertz. Resistance heating, we have seen this many times. Arc heating is another low frequency technique where you don't continuously produce heat. Instead, you produce an arc which generates a lot of uh, heat energy at a very high temperature, and then you use that. So in some cases, that is more preferred than supplying continuous heat. All methods can be direct or indirect. That's another way of looking at methods of heating. High frequency heating, there are two principal methods in general, induction type and dielectric type. I'll be coming to them slightly more in detail later. Low temperature is a word which is normally used for up to 400 degrees Celsius or so. Medium temperature is reserved for 400 C to 1150 C. These are rough guidelines, okay? High temperature is anything below 1150. So when you read literature, you should be aware of roughly what these words mean. Okay, this tree I have already shown you in a previous document, and we have already seen this already in different other settings. Microwave oven is also a high frequency heating technique. Okay, that was not mentioned in the previous slide. Although here they are showing it differently from high frequency techniques, but it actually uses high frequency. Induction heating, dielectric heating, and infrared heating are three high frequency heating methods. Microwave oven or microwave heating can also be called high frequency heating, although technique is very different here. Infrared is very, very high frequency, just below optical frequencies, but they are becoming popular also nowadays. And power frequency is 50 hertz or 60 hertz, which we have seen several times, can be either resistance heating or arc heating. Okay, there's a bit of repetition here. Live with it. Now, heating element that we use in geysers, what are the properties that it should have? It should have very high resistivity. Resistivity, remember the resistance is R equal to rho L by A. Rho is resistivity, which means opposite of conductivity. So high resistivity will help you in generating more heat for the same current going in. It is one of the fundamental requirements. You cannot use copper as a heating element for sure, because it has very low resistivity. It has to be made of carbon or some other material, nichrome, etc., etc. There are special materials that have been developed for this purpose. Other thing is this element should be able to withstand very high temperatures, obviously, without deterioration in properties. Of course, that doesn't happen for a long time. You have to change the element periodically. Low temperature coefficient, the properties should not change much with temperature. Positive temperature coefficient, that means resistance should increase with temperature. I don't know whether it's essential to have it that way, but fine. Free from oxidation at high temperatures. It should not, get oxidated at high temperatures. And with aging also, it should not get oxidated. Now, these things we have already seen. Direct heating, electric current is passed through the body. By the way, the material to be heated or body to be heated is also known as charge. Don't confuse it with electric charge. This is a word used by mechanical engineers for describing the material that they are trying to heat. It is just a word. It has no units, nothing. So charge means the material to be heated. If you pass the current through the charge itself, then it is direct heating. Efficiency is better. And one example is electrode boiler for heating water. I guess electrode is the one that is carrying current and it is immersed in water. Indirect heating means current is passed through highly resistive material, heating element placed inside an oven. And then in the oven, something else is kept nearby, which is the charge, the material that you want to heat. So heat gets transmitted to the material through convection or radiation or a combination. For example, room heater, they get heat to you through convection. Obviously, current is not passing through you, right? So it's indirect heating. Okay. Some repetition again. The charge, the material to be heated for practical reasons can be in powder form, or it can be small pieces, or it can even be a liquid. So depending on that, your method may have to be chosen correctly or modified suitably. The supply can be AC or DC. In AC, it can be one phase or three phase also. If it's a if it's a DC supply, then two wires will go in. If it is single phase AC, then also two wires will go in. If it is three phase AC, then more than two wires will be necessary. Delta connection will ask for three wires. Y connection will ask for four wires, right? Yeah, that's what is written here. Okay, so again repetition. Let's move forward. This is a diagram conceptually describing direct resistance heating. Two electrodes are immersed in the material to be heated, which is here in the form of pieces, small pieces. Okay, and there is an enclosure in which the material is kept. In the material, you immerse the electrodes on which you are supplying either DC or AC. To improve things, we also sprinkle high resistive powder on top of the material. That helps in generating more heat from the same electrodes. Everything else is electrically explained very easily. It's Ohm's law. I square R will work. Okay. Okay, again repetition. The enclosure is known as heating chamber. That's probably a better word for this. Heating chamber for the outside container. Now, in indirect heating, what you will do is you will have a heating chamber in which you will place the electrodes. But that chamber, in fact, the electrodes are not touching the material to be heated. The chamber is touching it. So the heat produced will first warm up the chamber, and then chamber will transfer the heat to the charge. Okay. It is less efficient, but sometimes it is preferred because it gives you a better method of controlling the amount of heat flow. If you think that the material is getting heated too fast, you will move this heating chamber a little bit up to reduce the heat flow. If you think you need more heat, then you will push it down the material a little bit. So you have better control. In direct heating, that control is not possible, except playing with the current value. Indirect heating has its own advantages, despite being less efficient. Heating element failure is hotspots are formed, which make it less functional. Oxidation, corrosion happens, or it can be simply a breakdown, cracks, and it's no more capable of heating. Arc heating is not continuous flow of electricity. Instead, we produce an arc, a very high intensity arc, for a very small period of time. There are, especially in industry, there are operations that require arc rather than continuous heat production, because you want very high temperature for a small period of time to get some operation done. Okay, this can also be direct or indirect, that is for sure. Electrodes can be carbon made, or there are other materials also, anthracite, coal, etc., to make them long lasting and defect free, essentially. Okay. Of course, the main portion of electrodes has to be conducting, where the connections are being made, but everything else can be made of insulators. So to improve the performance at high temperatures, we use these materials which are mentioned here. Oxidation starts at around 600 degrees Celsius. So carbon electrodes are generally not used above 600 degrees Celsius. There are other methods also. Graphite is also used, especially if temperature is much higher than 600 degrees centigrade. There is another variety called self-baking electrodes. I don't really know much about it, but I know that they are not natural materials. They are specially produced. They are basically produced using a paste of a material through which current is passed, which bakes the material and produces the electrode. This is how the operation is done to produce the electrode. Materials are the application of this kind of electrodes is for production of all these materials, ferroalloys, etc. Don't worry too much about remembering details. Just get a bigger picture. Now, arc furnace is obviously depending on production of arc inside a furnace. It's a giant kettle lined with heat resistance material. A lot of practical details here. You may not appreciate everything. Someday when you will see an arc furnace in industry, then you will appreciate how much work is there in designing it. At least you should be aware of these words, if nothing else. One important issue in heating materials is to stir them so that uniformity is maintained in heating. In some methods, stirring is inherent, and arc method is one of them, because the arc has tendency to produce electromagnetic waves which inherently stir the material. You don't have to shake the material physically to get heating done in a uniform manner. There's practical info here that power factor of a typical arc furnace is around 0.8 lagging. Fine. Alloy steel is manufactured using this kind of technique. It gives purer. There's a spelling mistake here. It's not PRER, it's PURER. Now, direct arc furnaces have their pros and cons. Okay. And they're simple in construction for sure. Product purity is better, but they are costlier. And energy required is much higher. Okay, so there's a lot of detail. Let me not go through each and everything, but at least the basics must be clear to you. What I want to show you is, besides arc furnaces, there's another technique. You can go through it once you get the PPT from me. This info is again meant for your future preparation, other than only for this course. You will see all these things in many other courses also. Indirect arc furnace, that means the material to be heated is not seeing the arc directly. Instead, the arc is being produced using electrodes which are away from the material, and then the heat produced by the arc is going to the material through convection. Okay. Okay, forget this diagram. Someday you will appreciate it much better than today. Now, dielectric heating, yes. So far, we have looked at only low frequency heating, 50 hertz or 60 hertz. Another variety, which is equally important, is high frequency technique, where frequency of the voltage applied is in megahertz typically. One of those methods is known as dielectric heating. Dielectric means wood, bakelite, all the insulation on wires that you see, these are all dielectrics. They don't conduct electricity very much. But for practical reasons, they still need to be heated to make them better materials. And that heating requirement varies from material to material, from application to application. And typically 50 hertz is not a good candidate for heating the dielectrics. It is the high frequency signal that does a better job. You want to heat dielectrics in a gradual manner to condition them or to develop properties that you would like to see. Okay. Wood panels, plates that you see in kitchen, they are generally given this kind of conditioning before they are sent to you. Oils, and so many practical applications are there. Even fabrics, clothes are generally given this treatment before they are released to the market. That makes them better products, as simple as that. Many medical procedures, I was telling you last time also, they require gradual heating of the body, of parts of body, and this is better achieved using high frequency, because high frequency gives you a method of controlling the heat being produced by changing the frequency, besides changing the voltage. Microwave oven, of course, is a special case of dielectric heating. Food is dielectric primarily. It is lossy dielectric. We typically use 2.4 gigahertz signal going into it, and the signal produces the required heat which cooks the food. Now, this is a conceptual diagram about dielectric heating. The material to be heated is sandwiched between two conducting plates, and I am showing rectangular plates here. They don't have to be rectangular, they can be any shape. Between the two conducting plates, you apply the necessary voltage with frequency that you can choose, typically in megahertz. The nature of the material has to be lossy, then only heat will be produced. Forget the diagram on the right hand side. I'll come to it a little later. But electric heating is conceptually described by this diagram all the time. If the material is lossless, you cannot produce heat. It is the losses in the material that are responsible for producing the heat. Here's some basic theory. When a capacitor is subjected to a sinusoidal voltage, the current drawn by it is never leading the voltage by exactly 90 degrees. A perfect capacitor, as we have seen in the past, has 90-degree phase shift between current and voltage. But for real life capacitors, there is always some loss. So they are not perfect. So the phase shift is less than 90 degrees. And that produces the loss. The angle between current and voltage is slightly less than 90 degrees. The amount by which the angle is less than 90 degrees is known as loss angle, delta. In a perfect capacitor, delta will be 0. And that means current and voltage will be perfectly in 90-degree phase with each other. For practical materials, delta can be 1 degree, 2 degree, 3 degree type of thing. So the power factor, which is cos phi, has an angle phi, which is 90 degree in a pure capacitor, which is slightly less than 90 degree in a practical imperfect capacitor or imperfect dielectric material. So delta and phi are related by this diagram because of that. Ideally, phi should be 90 and delta should be 0 if you have no losses in the material. But more the losses, more is the value of delta and less is the value of phi. And cos phi is the power factor. If delta is 0, phi will be 90 degree, cos phi will be 0. That means no dissipation of power in the material. If delta is high, phi would be much away from 90 degrees. So cos phi will be, it will start becoming more than 0 for sure. So heat will start growing in the material. This is why this diagram is important conceptually. Okay. Other thing is, I'll show that in a separate document, that if low frequencies are involved, you will see that heat is not produced in sufficiently large quantity. So high frequencies need to be used. Now, dielectric heating has these advantages. Uniformity can be maintained, low running cost. But by the way, it is very expensive to set up dielectric heating in the beginning. A lot of people avoid dielectric heating. A lot of people in industry avoid dielectric heating only because of the cost. But jewelers, the good jewelers, they still set up the whole thing to condition the jewelry using dielectric heating, which makes it beautiful as well as long lasting. So, it's a financial call ultimately, whether to go for dielectric heating or not. Big industries usually go for it. Even the furniture manufacturers, the large ones, always have dielectric heating at the end of their manufacturing process to make the furniture last longer and to make it look good cosmetically. If you want to heat it faster, that is possible by changing the frequency. But you got to be careful. Dielectric heating, if it is used for inflammable materials, you may see fire coming out. So it has to be applied with common sense. Don't allow too much heat to go in a material at a fast rate. Do it slowly. And of course, if you are dealing with a patient whose limbs you are trying to heat, you got to be super careful. You are dealing with a human being, But all that has been done. A lot of research has happened in this area, and things are under control. Disadvantages: high installation cost. I was telling you that already. And yeah, use it only when you absolutely need to use this method. Okay. There's a bit of mathematics in this method. I'll show that in a different document. Typical applications of dielectric heating are food processing industry. This potato chips and all those things that you eat, they have all been subjected to dielectric heating before they were put in the envelope, in the box. Wood processing, a lot of furniture that you see is actually conditioned using dielectric heating. Drying process in textile industry. The clothes that are made are quite wet to begin with. So to dry them fast, we use electric heating. Also, many more examples. Electronic sewing, I'm not sure how the electric heating works there, but there must be a reason why this is there. The food, if it is dehydrated, the packaged food I'm talking about, if it is dehydrated, it will last longer. So that dehydration is typically done using high frequency voltage. That is dielectric heating. Vulcanization of rubber, another practical application. Explosives that military uses are typically conditioned using dielectric heating so that they are dry and long lasting again. Heating of tissues and bones of body required for the treatment of certain types of pain and diseases. That definitely requires high frequency heating, which is dielectric heating. The removal of moisture from oil. This is a very practical application in industry. Oil has a lot of moisture. Dielectric heating can remove that moisture quickly. Okay. Okay. It is a conceptual diagram showing you what is done. You have a high frequency AC supply connected across the material to be heated. In fact, there will be some resistors also in the circuit to control the current flow, but they are not showing it for simplicity. Okay. Two electrodes for sure. I was showing you plates in the previous diagram. Here they are calling them electrodes. Fine, not a big issue. But typically two conductors, two conducting plates or conducting electrodes have to be there, which will take the AC input or DC input. Oh, sorry, not DC input in this case. It is AC input, high frequency AC input, which will supply high frequency current to the material. And because of the fact that material has losses, heat will be produced. This numerical example I am going to discuss in a different document. Okay. Now, induction furnace is a very interesting high frequency technique. This is very different from dielectric heating. Dielectric heating was using, what should I say, electrostatic effects. This method, induction heating, uses magnetic effects. What we saw in induction motors is what is being used here also. You short circuit a loop of wire, a high current flows through it, and heat is generated. Those currents are known as induction currents. Now, induction heating can be, so I suppose, at 50 hertz also, and it can be at high frequency also. I agree, no issue with that. However, in conventional power frequency methods, the heat is transferred by conduction or by convection or by radiation, where in high frequency techniques, the energy is directly converted into heat energy. This is a conceptual difference. For high frequency induction heaters, the induction effect directly happens in the material itself. You don't have to worry about convection, etc. And those high frequency currents produce the required heat inside the material. It is kind of direct heating. While low frequency induction heating is indirect heating generally. Now, two types of materials can be heated using this technique, conducting and non-conducting. Dielectrics can be heated this way also, by the way. And conductors can be heated this way, which was not possible if we were using dielectric heating. So for heating conductors, induction heating is the only method. And conductors may also need to be heated to properly bake them and to produce properties that you need. Okay. The heating of conducting materials, both ferromagnetic and non-ferromagnetic, is known as induction heating. Fine. That's fine. The insulating materials as we have already seen, we can use them, we can heat them using dielectric heating. So that part we know, don't worry about it. There are some numbers here. At what rate heat transfer occurs for low frequency techniques, etc. You see that for low frequency applications, you don't get much heat per square centimeter. But for high frequency cases, you get much, much higher heat. 10,000 watts per square centimeter can be produced if you are using high frequencies. That helps. Speed of production goes up because of that. Yeah, it is the transformers. Theory is the same for induction heating as we saw in transformers. There will be a primary winding through which an AC current will be passed. This winding will be magnetically coupled to the metal that you want to heat, and that metal can be called secondary winding. A metal is short circuited, so secondary is short circuited, which is what we saw for induction motors also, especially squirrel cage type induction motor. So an electric current is induced in the metal when AC current is passed through the primary coil, and that is how heat is produced in the conductor. I know there's a lot of detail here, but at least concept must be clear enough. Even if you don't understand all the practical construction details, fine. Now, in transformers, we always use a core to put the windings. In induction heating, we may or may not use a core. There are pros and cons. Coreless type induction furnaces are also available, and core type are also available. And core can be vertical, it can be in many different orientations. This is all practical detail of the in designing things. Charge means the material to be heated, is the single turn secondary coil of the transformer. Charge is coupled to the primary through an iron core. So we are talking about a core type of induction furnace right now. Typically, induction type of heating is done at a very high temperature. That's why we are using the word furnace. Temperature is generally greater than 1000 degree Fahrenheit. So I'm not using the word oven. But there are times when I suppose induction ovens are also possible. You never can discount the possibility. Okay. I'm trying to give you a picture of how these things are implemented. Here is one example. Primary coil is on the left side and the core is in between. We are showing the cross section of the core. And now on the secondary side, you have a container containing the material to be heated. And that container is connected physically to the core. The heat produced is transferred indirectly to the material to be heated. Okay. Now we are calling it direct because we are actually physically touching the hearth, that is the piece that contains the material. We are connecting it physically to the core. So heat is directly getting transferred. But from there, the heat would be transferred to the material that you want to heat. That is also happening through direct contact. So that is why the word is there, direct. And there is a core involved, so we are calling it core type. And we are assuming single phase supply, of course. Okay. Even if you don't want to read everything, it's okay with me. There's a lot of detail here in terms of practical implementation of various types of induction furnaces. In Jaipur, there are a couple of companies that actually have this furnace. I have visited them. Someday, maybe you will get a chance to visit them and see induction furnaces. Heat treatment to metal is done using these kinds of furnaces. It's a very practical industry application. Temperature range is from 400 Celsius to 1000 Celsius typically. Power factor is around 0.8 lagging.